Now we are going to start with the afternoon session. First, I want to give a short introduction in our relocalization challenge, and afterwards we will present the first and the second place of our submissions. And then we will continue with a presentation-only paper entitled Self-Supervised Domain Adaptation for Visual Navigation, which with global map consistency, which was presented this year at WACV conference. Afterwards, we are continuing with an invited keynote talk from Henning Lattigan, and we are doing a short coffee break, and our session will be concluded by a keynote talk given by Philipp Krähenbühl, and in the end we will have some closing remarks. So I want to give a short overview of the relocalization challenge we have been organizing since ECCV 2020 now, so this is the third edition of our event. And our visual relocalization challenge is based on the 4-season dataset, which was released 2 years ago, and we're covering 9 different scenarios in and around the city of Munich. And for our visual localization challenge, we picked 3 different kind of scenarios. One is depicted like city loop, another one Old Town, which is kind of showing Munich inner city, and a parking garage, which is a combined indoor-outer environment, very challenging for GPS denied algorithms. And we will have prize money, $1,000 for the first prize and $500 for the second place. So what you can see here is a point cloud visualization of the data set, and in purple the 6 degree of freedom trajectories. So basically we have a car traversing the streets, and we recorded all our sequences at different times of the day and also different seasons. So for the challenge we have those 3 scenarios, which is city loop, and this is a large scale traversal in the city of Munich, which consists of large street scenes and also a tunnel environment where obviously it's challenging for tracking algorithms and also for localization algorithms. The Old Town is really in the city center of Munich, and obviously this scene consists of very dynamic objects and a lot of pedestrians walking the street, and you have a lot of occlusions. So this is also a very challenging scenario. And the last scene is the parking garage. As I mentioned before, it exhibits combined indoor-outer environments where you typically don't have access to GPS signals. So in order to give you a glimpse about the different conditions on how challenging this dataset is, as you can see here is, if you look at the different rows for the different sequences, you can see that we cover drastically different environmental conditions, not only lighting and illumination changes, but we also do cover, for example, snow in the sequences for different seasons, and also day and nighttime changes. So for example, in the second row, the last image, you can see the illumination is quite dark, and you can almost don't see any features in the images, so it can be quite challenging. So how do we ended up in building the data set? So we are building reference maps. This is being done by visual inertial odometry, and we've used it with global accurate RTK GNSS measurements to obtain a globally consistent reference map. We capture the images with a stereo camera rig as being shown on the right side, and we basically get reference and target pairs which we use for relocalization. For the challenge participants, we provide reference and query frames to be localized, and the task is very simple here to estimate the relative 6 degree of freedom pose between the reference and the target pairs. We withheld the reference poses for the participants, and we evaluate the submissions by a submission to the organizers. How do we evaluate the submission? So the evaluation is basically done based on the pose accuracy of the method, and we do so by defining a set of localization thresholds on the position error, and we basically evaluate the translational error between the estimated and the estimated reference pose. And for each threshold, we report the percentage of the localization candidates which were localized within the given thresholds. So this time around, we received a couple of submissions to the workshop, and as you can see here, what is depicted is the method and the recall at different localization thresholds of 10 centimeter, 25 centimeters, and with 1 meter. And as you can see, the first method, which is called CyberLoc, towards accurate long-term visual localization, it achieved astonishing results. So they almost achieve 100% in all recall measurements. So we are very interested in hearing this talk. The second method is called the real-time fusion framework for long-term visual localization. And as you can see here, already the gap is quite significantly. The third place is self-learning semantic-aware local features for long-term visual localization. And last submission is HLOC plus laughter. At this point, we also want to thank our workshop sponsors, Artisans and Kudan, for making the prize money available and allowing the distribution of the prizes.